transforming sinusoidal functions. So we just talked about sinusoidal functions. Now we're going to work on transforming one, which is this part here and what these values do. Now our A value is essentially what our amplitude is. Okay, it doesn't stand for amplitude, but it just so happens it deals with vertical stretches and compressions. Okay, vertical stretches and compressions, which if you remember quadratics, it had a very similar letter for it, right? And it just turns out that A is actually going to be equal to our amplitude also. Okay. So just to keep that in mind, that will really help us when we're trying to solve our amplitude. Our K here deals with horizontal stretches and compressions. Now I'm not sure if you've seen a value of K before in a function. Have you ever seen
in other
other functions? Okay, so it's the same idea. It's going to deal with stretches and compressions along the x-axis or horizontally. C will deal with transformations horizontally, and D will deal with vertical transformations. Okay, so we'll just call those both T. So what we're going to do is talk about how they can affect our wave. And again, we're always going to be referring to our original one, which is our sine x. I'll quickly put it up here. So here's our original wave. Now, when you're first dealing with these, it's usually easiest when we're given a value of something. So let's say I've been given a function that looks like this. F at x is equal to 3. I'm just going to make this up. Sine K will be do I guess 2 in this case. X, we'll say plus 90. We're working with degrees. And if it's 3, we'll go to minus 2. Okay. So I've already color coded this, so we know what A, K, C, and D are. Okay. So we'll talk about how they're going to affect everything. Now, first of all, it's usually easiest if we deal with our A and K first when we're set along our equation of the axis of 0. It doesn't matter, we can technically transform, so move the wave to wherever it has to go, and then deal with stretching it or making it longer, like in this fashion. But that can be a lot tougher when we're not along the axis, so it's usually best to maybe work with these two first. The first one I'm going to work with is our A value, okay? And our A value is going to do with vertical stretches and compressions. So really, and the reason it's easiest to work with this first, if we stay on this x-axis, what we can do is we can multiply all of our y values by a, so a times y, to give us the new y values. We'll call them y1. Okay? So what I mean by that, for instance, what is the y value here?
0.
0. And what would 0 times 3 be? 0. So it didn't change. It's at the exact same spot. Now the y value here is 1. What would be if we multiply that by 3?
3.
It'll be 3. So now our new y value is up here at 3. Then again, 0 times 3 is 0 again. So what you're hopefully going to notice, and then negative 1 times 3 gives us negative 3, is that our points of 0, they actually don't change. Okay. So to start, these types of x-intercepts don't make any difference. Okay. So this would be the function. I'm doing my best here. It's a lot farther than normal. Come down. So if you notice, this has been stretched by a factor of 3. Okay? So a big change to the original one here. Not perfectly drawn, but a big change. It's been stretched by a factor of 3. And this would actually only represent f at x is equal to 3 sine x. Okay? I've only put one thing into it. Everything else has stayed the same. Now the x value we want to work with, okay, we're going to keep that same stretch. So I'm going to call it 3 sine, but in this case, I'm going to put 2x. Okay, so we're going to deal with our horizontal compressions and stretches. Okay, now I'm not sure if you've done these before, but when you're talking about horizontal, it's kind of the opposite of what our vertical compressions would be. So in this case, it looks like we have a factor of 3, right? So we got stretched. Because our k factor is 2, we actually don't get stretched, we get compressed by a factor of 2. Okay, so what we're going to do is we're going to take all of the, again, x values, and as long as we're on our x-axis, this can be really easy to do. We can divide all of the x values, so the y coordinates at their x values, and we can divide them all by 2 to figure out where they are. Okay, so we're going to divide them by 2. And really one way they tend to write this is they'll give you something like this. You do a times your x values and k divided by your y values divided by k. Sometimes how they would represent it if you're talking about a vertex or something. But you can do this to any point on a graph. Okay, so what that means is, for instance, 0. What is 0 divided by our value of 2?
0.
Still 0, so this point doesn't move anywhere, okay? And that's what makes it easiest. We're really working from the origin when we start this, without transforming. If we transform this first, this style we're doing doesn't technically work, okay? So the very first value is 90, and our 90 value is 3. Well, what is 90 divided by 2?
45.
Yeah, so that's going to be halfway up there. So our 3 now moves over to 45, okay? 180 divided by 2 is going to give us 90, so that 0 moves over to here. Okay, 270 divided by 2, it's going to give us, is it our 180? No. 145? Let's get a calculator for that value. Divided by, no, it's the wrong button. 135. Actually, what you want to think of it, yeah, I guess, okay, that works. And the easiest way to do this is just to take every single value and compress it by half. So half of this, if you're counting points, 1, 2, 4, 5, 6, we would just move it back 1, 2, 3. Yeah, here it is, 135. There it is. 360 ends up where 180 is. Okay, so what this has done, and we should have talked about first of all with our A. Our amplitude obviously changed to 3. We talked about how A was the amplitude of 3. Now what's happened here is this has been compressed. Remember we talked about the period of the function? The period of this function has changed immensely. The period is no longer 360 degrees. We got back to 0 in only 180 degrees. Okay, so this is going to affect the period of our function. And what we can always do is take the original period, in this case it was 360, and divide it by the k value. So if the k value is a whole number, our new period became 180 degrees. Okay. So that's going to repeat that pattern. This one will go up to 3, back down, down to 3 here, and this is going to continue in this fashion. Okay. Now this is going to get a little messy. So what I'm going to do is I'm going to get a program that's going to help us out to keep this all clear. Okay. So I'm going to pause this for a second. Okay, so like we said, it got a little messy here. So I'm going to go over this program, and here's our sine wave. Now the reason I didn't show it to you here to start is because this one's kind of going by hundredths. Okay, I suppose I can affect the scale. No, I don't think I can affect what the actual scale is going up by. It only has to do with zooming, okay? So, you know, that's roughly 90. This is about 270. Like, we have an idea where the peaks, the max and mins are, right? So let's talk about what the next one did. The first one we did, we decided to do 3 sine x, right? And we can already see how that has affected the stretch. It's gone up 3 values, but our x-intercepts ended up being the same. The next thing we did was 3 sine 2x, okay? And it compressed it. It made this guy come in out of the periods by essentially dividing it by 2. Okay, so we've moved those in by 2. And then the next 2 things we're doing, which are a lot simpler, but we can kind of get rid of these for now. We don't need to look at them. 3 sine bracket 2x. What was the value we had? What did we say? Plus 90 and negative 2. Okay, so first one is plus 90 degrees. And what's going to happen, because I am going to turn this one back on, is if you notice, from the blue one, first we'll have the blue one, that was our 3 sine 2x. In the next one, it shifted it. Now, it looks like it could have shifted it to the right or to the left, but because it's a positive value, it actually shifted it to the left 90 degrees. Okay, so we started here at the 45 and 3, and then 90 degrees to the left of that would be negative 45 and 3. So it shifted it to the left 90 degrees, okay? So turn off the blue one there. And then finally, the last movement we had was sine 2x plus 90. Do we say minus 2? I think we said minus 2, yeah. And in the minus 2, what we've noticed is our 45 and 3 has now been shifted down to 45 and 1. We've gone down 2 in terms of value. Okay, so from the original one, all of these movements occur. Okay, so we'll talk about one at a time. So the first thing we did was stretched it. Okay, then we compressed the horizontal axis. We shifted it 90 degrees to the left, and finally we pulled it down 2. So looks very messy, but in the end, this is our final graph here. Okay, so that's what it is. We're transforming the function the same way we transform any other function. We just have to use, in this case, we're using degrees, and eventually I think you guys will get to radians.